Hello all, my name is Matthew Griffin. The information I'm about to present was created in cooperation with faculty advisor Fernando Del Amo Gonzalo at Keene State College. For this presentation, we'll be learning about advanced building facades and indoor air quality, the building science that will guide the future of architecture. This presentation will explore building science principles that will begin to combat COVID-19, the climate crisis, and more. To start off, I have included this table of contents that reviews the topics we will cover today. We will begin by reviewing material from my first of two publications, Glass Facade Technologies Module 1. In this publication, we will analyze curtain wall technology, which will include stick and unitized types, as well as structural glass, double skin facades, and the integration of renewable energy technology into curtain walls. Then we will review material from my second publication, Thermal Conditioning and Sustainable Design in Building Design. Here we will discuss bioclimatic design principles, zero energy buildings, and finally end this section by having a discussion on indoor air quality, or IAQ, and its connection with the ongoing COVID-19 pandemic. Finally, we will conclude this presentation by discussing climate change concerns and discovering the future of these technologies. So let's begin by learning more about the building science surrounding advanced facade technology. The information in this section will be pulled from my recent publication that I helped to co-author, Glass Facade Technologies Module 1. For this project, I collaborated with Dr. Fernando Del Amo Gonzalo, an associate professor at Keene State College, to help produce the English translation of this text. In order to do this, we collaborated with Benito Loret Aguirre Gaviria, an associate professor of the Master in Facade Technology and Sustainable Envelopes program at the Polytechnic University of Madrid. So what exactly is a curtain wall? A curtain wall is an outer covering of a building where these walls are non-structural. Typically, a curtain wall is constructed by creating aluminum horizontal and vertical elements, otherwise known as mullions and transoms, that hold glazing. These aluminum elements are anchored to the slab of the structure. From these anchors, the curtain wall is draped against the structure of the building, hence the name curtain wall. Since this type of wall is non-structural, it can be made of lightweight materials, reducing construction costs. Curtain wall technology is broken down into two types. The first type is known as the stick curtain wall. This is a curtain wall in which elements are assembled on site. The mullions are anchored to the slab first, then the glazing components are locked into place on the mullion track. Here we can see an image showing how glazing elements are fastened to the curtain wall structure by means of vertical mullions and horizontal transoms. The second type of curtain wall is known as the unitized curtain wall. This system involves having the anchoring system placed on the slab first, then placing glazing panel modules onto the anchors themselves rather than mullions and transoms. This system differs from stick curtain wall technology because the glazing panel modules are constructed in a factory, then shipped to the construction site, where the modules are then placed. This allows a greater level of precision compared to the stick curtain wall. Structural glass is exactly what it sounds like, using large glass panels that usually bear some weight in the structure. The earliest example of structural glazing is the Crystal Palace, which was built during the World's Fair in London, England in 1854. A modern day example of this type of technology would be the Fifth Avenue Apple Store in New York City. Double skin facades. Traditional building facades typically have one layer of glazing, while double skin facades have two, hence the double skin name. Double skin facades have several benefits, including aesthetic appeal as well as more practical benefits such as providing better energy performance, providing natural cross ventilation, building security, acting as a pollution barrier, showcasing daylight and views, and finally reducing wind and exterior sound. A case study for double skin facade technology can be found at the Terence Donnelly Center in Toronto, Canada. Here we can see the aesthetic value from this flyover of the structure. On the picture on the right, we can see the construction details of the facade. We will notice here that the interior division is comprised of an insulating glass and an extruded aluminum unitized facade frame. On the exterior layer of the facade, we can see a monolithic tempered glass pane being employed, all secured by a steel outrigger and laminated tempered glass floor that connects the outer layer to the floor slab of the structure. The fascinating part about curtain walls is the fact that it creates a grid system in which wall elements can be placed in. Typically, glazing units or spandrel panels are placed into these grids, However, recently, architects and building scientists have begun to integrate renewable energy production into curtain walls. This technology turns buildings into energy producers rather than simply energy consumers. In addition to this, this technology enhances the energy performance of a building. So the next topic we're going to explore involves the work in my second publication, Thermal Conditioning and Sustainability in Building Design. The material in this section of the presentation will focus on sustainable design principles, IAQ, and the connection between IAQ and COVID-19. For this project, I once again collaborated with Dr. Fernando Del Amo Gonzalo, Associate Professor of Architecture at Keene State College. In addition to this, I worked with Roberto Alonso Gonzalez Lescano, Sonia Cisteros Garcia, and Felix Arumbu Gabiola, all of which work at large Spanish universities. My contribution to this project involved creating an English translation, creating images and diagrams, and developing the text itself. The first topic we will review in this section is bioclimatic design. Bioclimatic design considers the local environment and climate conditions. It takes full advantage of sunshine, winds, orientation, and constructive and formal resources, so that it is able to create comfortable living areas with the lowest energy consumption possible. Examples of these principles can include utilizing techniques and technology such as solar control, solar chimneys, use of thermal inertia materials, etc. The images that are shown here showcase some of these bioclimatic principles. Zero energy buildings combine energy efficiency and renewable energy generation to consume only as much energy as can be produced on site through renewable resources over a specific period. Achieving zero energy is an ambitious yet increasingly achievable goal that is gaining momentum across geographic regions and markets. In order to achieve a zero energy building, several strategies that are both active and passive in nature must be utilized. These strategies include things such as installing renewable energy sources such as photovoltaic panels, constructing and maintaining vegetation walls, and employing bioclimatic principles. In the image provided, we can see a section of a zero energy building and the different strategies employed. Indoor air quality, otherwise known as IAQ, is the measurement of the health of the environment within structures. It is important to assure that there is a healthy IAQ in a building, otherwise occupants can begin to develop illnesses. Ensuring a high level of indoor air quality is not an easy task. IAQ is determined by 4 attributes: temperature and relative humidity, CO2 concentration, PM 2.5 levels, and existing TVOC. Temperature and relative humidity of a space are 2 important factors in the IAQ equation. Using these values, we can plot them on a psychrometric chart, which is the chart pictured here. Psychrometric charts are complex graphs that can be used to assess the physical and thermodynamic properties of the atmosphere inside a building at a constant pressure. Mechanical engineers and building scientists use these charts to determine what value of several variables is needed to reach the comfort zone, or the zone in which humans will feel comfortable with the ambient environment at a resting activity level. In the chart shown here, we can see where the comfort zone is located on the chart. It is estimated at 30 to 70% relative humidity and 70 to 75 degrees Fahrenheit. Another important factor involved in determining the IAQ of a building is the CO2 concentration. Work on IAQ adopts CO2 concentration as an index of indoor air quality. High levels of CO2 above 1,000 parts per million, which corresponds to a ventilation rate of approximately 8 liters per second per person, often indicate poor ventilation in the presence of other pollutants. A third important factor in determining IAQ of a building is understanding the amount of PM 2.5, or particulate matter below 2.5 microns or less, is present. PM 2.5 particles include airborne particles that are solid or liquid substances suspended in the airstream and can include dust, fumes, smoke, microorganisms, mists, and fogs. These particles can vary widely in diameter, with the most harmful in the domestic environment being respirable suspended particles, or RSPs. Controlling and maintaining a low PM 2.5 presence is vital to improving and maintaining respiratory health for building occupants. VOCs, or volatile organic compounds, are organic chemicals that have a high vapor pressure at ordinary room temperature. This means that these compounds can aerosol into the environment easily, possibly causing respiratory problems in building occupants. VOCs are numerous and dangerous. They can include both man-made and natural chemicals. Nearly 900 VOCs have been identified in the indoor environment. TVOC is defined by the standard ISO 16000-29 as a VOC mixed gas comprising of 40 individual compounds. Obviously, there is a huge concern between illnesses and indoor air quality. Recently, in trying to combat the COVID-19 spread, building scientists have been recommending the installation and use of HEPA filters. HEPA stands for High Efficiency Particulate Air Filter. This type of filter can theoretically trap and remove at least 99.97% of pollen, mold, bacteria, and any other airborne particles with a size of 0.3 microns. Here we can see a picture of how these filters work. Air flows through the redundant use of several layers of filter medium. This layering of materials allows the HEPA filter to capture as many air pollutants as possible. In conclusion, advanced building facades and thermal conditioning principles are two important aspects of building science that can and will radically influence the way in which buildings are designed and constructed. Currently, several severe dilemmas face the human race. Continuing development and research into these topics can help to reduce these ailments. The climate crisis is one of the biggest problems facing the college-age population. Improving research and technology in the advanced building facade sector will provide a higher level of energy performance of buildings. Using cutting-edge engineering technology in our facades will allow buildings to improve thermal performance, become much more airtight and insulated. Advanced building facades will also create a sustainable approach to construction, as many new buildings are employing carbon-storing materials that will greatly reduce the carbon footprint of our cities. Advances in this technology will also surely allow architects to develop new and exciting approaches to facade design and reduce overall CO2 emissions. The continued integration of renewable energy products such as solar panels will continue to reduce energy requirements on the power grid system and allow buildings to reach the net zero goal. Finally, the use of HEPA filters for natural and mechanical ventilation will ensure that future potential diseases will not be able to spread through multi-use buildings easily. As time goes on, there surely will be developments in these technologies. New and improved glass technologies are continuously being developed. Using micrometer layers of materials, engineers can create glazing panels that have several properties, such as holding more solar energy or rejecting solar energy, that will be continuously developed to serve the needs of architects, building scientists, and engineers. As we are all experiencing it, COVID-19 has radically changed the way in which we live for the past couple months. Not only affecting our daily lives, COVID-19 has had an impact on the building science world. The COVID-19 pandemic has and will continue to create a rush of research into how to create, sustain, and manage internal building environments that support a healthy indoor air quality. In addition to this, research into the ventilation rates of rooms and buildings has been reevaluated. Currently, building scientists are developing research to the perfect rate of ventilation for our buildings. The work that has appeared in this presentation is the culmination of research developed by Fernando del Amo Gonzalo, Benito Laura Aguirre Gabarria, Roberto Alonso Gonzalez Lescano, Sonia Cesteros Garcia, Felix Arumburu Gabiola, as well as myself, Matthew Griffin. Thank you for attending this presentation.